First, in part 3, let's take a look at the workflow from the photography methods to create 3D images and how we can use Metashape to create a 3D model from that image. Please choose how to participate in this session according to your digital environment. If you are using your own PC and it has enough space, let's create a 3D model by yourself following the instruction in the video. First, please download an Excel file and some photo data from the library on the e-learning page. You can find this data in the folder named Unit 3, Reference Materials for CP Photography. If you don't have a PC for the practice, watch the video and learn how to create a 3D model. Let's now talk about the photography methods to create 3D images for SfM-MVS. First, let's take a look at the camera setup. I recommend the following setting when using a camera that can have a detailed setup such as a single lens reflex. 1. Set aperture or f number from f8 to f11 to be just enough to prevent diffraction. 2. Set sensitivity or ISO sensitivity at 100 or 200. The lower, the better. 3. Set recording format at the highest quality with JPEG and RAW. 4. To accurately reproduce colors, if you have a grey card, shoot it to adjust the white balance. 5. Shoot without changing the focal length. Therefore, the distance from the artifacts and archaeological remains to the camera must be fixed to shoot. 6. If using a zoom lens, the focal length must be fixed to keep it from changing. 7. Use a tripod. Now, let's talk about photography basics. 1. Shoot the artifacts and archaeological remains with a 40% to 60% overlap of the shooting range. 2. Focus on the subject. 3. Make sure the picture is not blurry. 4. Make sure there are no parts of the target subject that are not visible. 5. Make sure the subject is in the center of the composition. 6. Make sure the distance to the subject is fixed overall when shooting. 7. Make sure to shoot up close if the details need to be 3D modelled. Let's talk about the shooting position for SfM-MVS. If the subject is flat, like the figure, don't shoot from one position, but shift the position while fixing the distance from the artifact and shoot several photographs. If shooting a rectangular space, like the figure in the middle, shoot 360-degree photographs. For artifacts like the bottom figure, also shoot from all angles. For all photography methods, a more detailed 3D image can be created by overlapping the images by 40 to 60%. Let's now move on to aperture. An aperture can be shown by f number. When using a single lens reflex camera, like in the picture, you can change the aperture by selecting M for manual mode, or A mode, acronym for aperture priority mode. In any case, the aperture, or f number, is recommended to be set from f8 to f11. Let's take a look at the differences in images per the aperture setup. The background with f2.8 may be blurry, but you can obtain a clear background with f22. In the case of shooting cultural properties, I recommend setting the aperture to the middle. If your camera has a range of f2.8 to f22, then set it up to the middle value, around f8 to f11, and take the picture. For reference information, we have videos like these. It is in Japanese, but you should be able to understand the workflow and methods by watching these videos. I would like to tell you how to save the photography data. First, create a 3D specific folder on your computer. Here, we name the folder Practice as an example. Create Out and Photo folders within the Practice folder. Out is the folder to store the completed 3D, and Photo to store the photography data as materials. Let's store the photography data taken to create 3D in the Photo folder. Now that we have gathered the photography data, let's try taking a 3D measurement of cultural properties with SfM-MVS. Let's take a look at the methods to create a 3D model by using SfM-MVS from the photos taken. The goal of this lecture is for you to learn the basics of 3D measurement using SfM-MVS. Specifically, you will 1. Have an understanding of exactly what SfM-MVS is. 2. Understand the process flow using Metashape. 3. Know the basics of photography using SfM-MVS. 4. Each of you will take your own photos and create a 3D model. Aside from the explanations here, there are other applications and complex applications. But let's first start by gaining the number 1, basics. Now, for anyone wanting to actually create a 3D image using your own computer while listening to the lecture, please download the GPS data and photography data I took for creating 3D models from the library on the e-learning page. Next, download the professional version of Agisoft's Metashape from the following URL and install it on your computer. For anyone using Windows 10, that is a 64-bit OS, so select Windows x64. The screen of Agisoft's Metashape website is like this here. Please download the professional version and install it on your computer. In any case, a 3D image takes a lot of memory and may be impossible to create on your computer, or take a long time. In that case, please see the process on this video lecture to understand the workflow. Start Metashape. A screen like this will be displayed. Select the bottom, Demo Mode. This demo version can implement basic analysis for free anytime. However, it unfortunately cannot save projects or output 3D models. Using the demo version, you can check basic work and check to see if a computer you own can analyze it or not. Also, as well as the demo version, there is a 30-day trial version in which you can use all the program functions. The trial mode can store projects and output 3D models, but you will be unable to use it after the 30-day trial period. In order to obtain the funding to purchase this program, it might be best to first practice the process and photography using the demo version to get sufficiently familiar with the SfM-MVS process. Download the trial version and use it to process a cultural property that you want to implement 3D measurement of within the 30-day trial period. Then, show the 3D model of this cultural property proudly to your colleagues and superiors saying, "Look how much we can do with this." Metashape will start. To see a 3D model more easily, you can change the screen color. Find Theme under Tools, Preference, General to change. The language can be changed. Go to Tools, Preference, General, Language to display the languages. Metashape's manual is also available on Metashape's website. Also, various websites offer tips on how to use it, most of which are written in English. That is why the English language is used in the menu here. Set the view mode of the 3D model to Ortho. You can change under Model, View Mode, Perspective Orthographic. A general workflow of creating a 3D model using Metashape is as follows. 1. Upload photos to Metashape. Steps 2 to 5 will be automatically implemented by the software, but those processes will be shown in the lecture. 2. This process aligns the photos. The software calculates the direction and position of the shoot. 3. Build a dense point cloud. This creates a cloud of detailed point data made from the pixels of all of the photos taken. This point cloud will be the basis of the 3D image. 4. Structure a 3D polygon model. This task creates various surfaces from the point cloud in process 3. 5. Texture the subject. Paste image data, such as the colors of the various surfaces in process 4, to create a 3D image. 6. Add positional information. 7. Create an orthophoto map. 8. Export the results. Process 6 and 7 are functions only available in the professional version. Now, let's take a look step by step. Add all of the image groups to be analyzed into Metashape. Select from Workflow, Add Photos. Select all of the photo images of the demo version that I have provided. Then left-click Open. To make one 3D image, we have taken 42 photos here. Although it may depend on the size of the subject targeted, since a photograph must be taken from all directions, I recommend taking as many photographs as possible to make sure there are no missing spots. The results after adding photos. The bottom of the screen displays the photos added. Save the project. Left-click File, Save As. However, saving a project cannot be done on the free demo version software. Here, just keep in mind how the project can be saved. The photo data folder is named dairy_text and saved in process 1. The file type is saved as Metashape project ***.psx close brackets in process 2. Next, we'll check each photo and delete any photos not needed to create 3D images. To confirm the photos, double-click the thumbnail of the photo on the Photos screen. Check to see if there are any unneeded photos, and delete any that are blurry or not needed to create a 3D model. Step 1. Left-click the unneeded photos to select them. Step 2. Left-click the cross icon to delete. A tip here to faithfully reproduce the real colors when you are shooting is to include a grey card for shooting in the photography for SfM-MVS. A grey card is a sheet to show accurate colors over the projected image. By shooting an image with and without a grey card, you can accurately show the colors of a projected image without a grey card on image software. As seen in the picture here, a grey card must match the face of the subject. The right picture is an image that has adjusted the white balance using a grey card. As you can see, a 3D model of a cultural property can be made using the correct colors. Now, let's take a look at the remaining tasks. Next is the task to create an alignment of 42 photos that were uploaded. As we mentioned in part 2 of the lecture, creating 3D by SfM begins by calculating the position of the shooting camera and creating a rough point cloud of the subject. The necessary steps for this task will begin in the next slide. First, left-click Workflow, Align Photos. Now the screen shows the settings window for the analysis. If the computer has a high specification, that is, Core i7 or higher, then set the accuracy to high. Set to medium or low if any lower. My Archaeological Research Methodology Laboratory regularly creates 3D models from TIFF, so the accuracy is set to the highest. Other settings are as shown on the screen. The image data provided to you are all small for practice, so they can be analysed regardless of whether the laptop is old or new, high spec or not. If fully analysing in a real situation, larger sized images will be used, so a desktop computer is recommended for the processing. Results of the Align. Images of the archaeological remains are represented by some dots. In order to check whether all 42 images have been aligned, left-click the triangle icon that is on the tip of the blue arrow to show detailed information. Additionally, there is a method to check the shooting position of the 42 photographs. To check the shooting position, left-click the camera icon at the top of the screen. To hide the shooting position, left-click the camera icon again. This can approximate the remaining position and photos necessary to be taken. If a 3D image could not be created successfully, check the remaining area required, shoot the photo, and then add. By left-clicking the Resize region from the menu icon at the top of the screen, you can check and change the analysis range. This shows before and after. This has been changed to an image with a slightly expanded analysis range. Next is Process 3, the Build Dense Cloud task. In this task, we'll create the base data of the 3D image by building a dense cloud from the rough point clouds generated from SfM and creating more detailed data. Select Workflow, Build Dense Cloud. A settings window for analysis like this will be shown. We will set up like the image shown on this slide this time. Set the quality to high if the computer is relatively high spec with Core i7 or higher, and set to medium or low if lower. At my Archaeological Research Methodology Laboratory, the quality is regularly set to high. The depth map filtering mode is set to aggressive. You can switch the view of the result of the Build Dense Cloud by clicking on the icon in the yellow rectangle. Next, we will proceed to the task to create a surface from the many points generated in Process 3. This is called the Build Mesh. Through Build Mesh, we will create 2D surface data from the points. Left-click Workflow, Build Mesh. Then a settings window for analysis will be shown. Set to high if the computer is relatively high spec with Core i7 or higher, and medium or low if lower. We analyze at high at my laboratory. We will take a look at the results of Build Mesh. Check to see if there are any gaps or missing data in the necessary parts. If there is missing data, then that portion will not be shown in the image. Select this icon to omit the color of the model. This view will make it easier to check for data loss. Finally, we are at process 5, Build Texture. And here, we'll do the work to add information such as colors to the surfaces created in process 4. Left-click Workflow, Build Texture. On the Setup screen, choose Generic for mapping mode and Mosaic for blending mode. Set up the texture size count to 4096 by 1. Then, click OK with this setting. Click the image icon and select Model Textured. Then it will switch to displaying the created texture. This is the completed image. You've created a 3D model. The basics of controlling a 3D model are to left-click while moving the pointer to rotate, and right-click while moving the pointer to move, and roll the mouse wheel to zoom in and out. Additionally, if you want to check the analytical information of the 3D image, right-click the chunk you want to check and left-click Show Info. By doing so, you can check the duration required for the analysis and the analysis settings. In the professional version, you can output more detailed information as a report in PDF format. Next, let's take a look at a method to select and delete unneeded parts of the completed 3D image. For example, if the top portion of this image is not needed, left-click Rectangle Selection. Surround and select the unneeded part while holding down left-click. In this way, left-click Rectangle Selection. Surround and select the unneeded part while holding down left-click. Press the Delete key or cross icon to delete. The result of the deletion will be this data. How was the process? Were you successful in creating an image on your computer if you were using the demo version? In the next lecture, we will talk about how to use this 3D image. Let's now talk about the second part of creating 3D models using Metashape. Here, we will take a look at how to create a georeference, which provides coordinates to the 3D image, and how to create an orthomosaic that can remove the distortions to the created 3D image and create orthographic images for use in producing a horizontal projection. First, let's talk about georeference, or the task of providing coordinates to a 3D image. By adding coordinates, you can understand information such as the actual size and distances on the 3D image. In order to add coordinates to 3D data, several sets of GPS data from the target archaeological site must be obtained in advance. Here, 5 targets were set up and prepared by inputting these 5 GPS data points into Excel in advance. For anyone who wants to actually practice with the Excel data, you can do so by downloading from the library on the e-learning page. For those who do not practice, please learn through looking at the PowerPoint images. First, at the bottom left of the Photos window on the screen, select one photo showing the target black and white board that is the GPS point. When creating a 3D image, always make sure to separately shoot a photo that shows a GPS data point. Double-click 09270038 to enlarge. This is the result. You can confirm target number 1. Use a mouse wheel to zoom in and show the center of the target. right-click at the center and select Add Marker from the menu shown to create point 1. This is the result after adding a marker. Likewise, add markers to the second and so on, all the way to the 5th target. Left-click Model, shown in the yellow rectangle, to return to showing the 3D model. Then click Model. By clicking on the flag icon surrounded by the yellow rectangle at the top of the screen, the markers that we set up will be shown. In order not to show, re-click the flag icon. Check the layout of the markers by showing the 3D model. If it is like what is on the slide, then it is okay. If it did not work, try it again. To delete the marker, right-click on the marker to show a menu and select Remove Markers to delete. A 3D model created by SfM-MVS does not initially have the size and position information of the 3D model. So, we can use these targets to add size and position information from the GPS data. For artifacts, we can use a ruler or the like to add the size. If the marker is not shown or is displayed incorrectly, add the marker again. To delete the marker, right-click on the marker to show a menu and select Remove Markers to delete. Now, we will begin placing coordinate data into the points. Click Reference at the bottom left of the screen to switch to the Reference Coordinates window. Click Import at the upper left of the reference window to import the reference coordinates on Excel. Select and open IDO_GCP.CSV as the reference coordinate file. If you are practicing it now, please open the Excel file that was distributed by the instructor. Set up like this and press OK. For some additional explanation, the top one is the coordinate system. This is information to show where on Earth the 3D model is located. The second one is how to separate the data. Coordinate files are basically created by CSV files. This time, we will separate the file by commas, so select comma. CSV files are prepared and created by Excel or Notepad. The bottom column is the preview screen of the load-in. The name, north-south, east-west, and height of the points will be loaded in that order. 1. Tick all the boxes next to the flags. 2. Click Update Transform to reflect the coordinates to the 3D model. The resulting part that is surrounded by yellow shows the differences. We can see that the difference is about 2 centimeters. The equipment that measured this target was a GNSS surveying instrument, and since the accuracy of this method is about 2 centimeters, we can say that the 3D model created by SfM-MVS is sufficiently accurate. The equipment used to measure the GPS is an important factor that affects the accuracy of the 3D projection image. We have now been able to add the coordinates to locate the 3D model on Earth. Next, let's take a look at the method to create an orthomosaic that can make orthographic images for the rough sketch of a horizontal projection image. This task is to remove the distortion to the 3D image and recreate the data so that we can create a horizontal projection image via tracing the photo. Select Workflow, Build Orthomosaic. As on the slide, choose the resolution of the ortho image you are creating and click OK. First, Step 1. Switch the window at the workspace at the bottom left. Next, Step 2. Double-click on Orthomosaic. Export the ortho data. Left-click File, Export, Export Orthomosaic, Export JPEG, TIFF, PNG. A dialog box will be shown, so set up like on the slide and left-click Export. Choose where to save, such as desktop, and name the file. Here, we name it dairy_ortho, and select the file type, TIFF/GeoTIFF. Then save it in any folder we want. Here, we choose the Out folder, which we have initially set up to save the complete 3D images. It is convenient to create a folder at the very beginning of the work to save these final versions on your computer. We have so far looked at the tasks to create accurate horizontal projected images. Next is finally how we save a 3D model with the correct size information. Left-click File, Export, Export Model. Here, the same as before, select the Out folder to save the completed data. Name it Textured, and save the file type as *.obj. Then, a dialog box like this will appear. So set up like this screen and left-click OK. The saved ortho image is now a 3D image. This can be displayed, edited, analyzed on GIS software such as QGIS. In addition, this 3D model can be displayed, edited, and analyzed using an open source program such as Cloud Compare. What has been explained so far is how to create 3D images. Were you successful? Here is a little tip. If the original image was different, would there be differences if the same archaeological site was analyzed? As a way to save, there is the TIFF developed from RAW and JPEG, for which the data amount is small. A 3D model created from TIFF has a higher quality than a JPEG image that was developed from within a camera. In this case, for example, on the left is an image created from a JPEG, and on the right is an image created from TIFF. You can see that the one on the right clearly shows each rock and is more detailed. When shooting, I recommend to always record using both RAW and JPEG. Additionally, there are merits to develop from RAW to TIFF. As explained earlier, if there are 1 or 2 photos with a grey card, the white balance is adjusted and you can create a 3D model of the cultural property with accurate colours. On the right is a reproduction with the correct colours. Even the colour information can be correctly recorded. Aside from this, the information volume and processing time to create the 3D are different for TIFF images and JPEG images. A model created from TIFF has more information volume compared to a model created from JPEG, thus having a greater analysis load and processing time. Currently, the differences in this time are becoming smaller. This concludes my lecture. For anyone interested in 3D modelling, please request practical training with ACCU next. I hope to hold the on-site workshop in your country in the near future. Thank you.